A classmate and I thought it would be a cool idea for the class if we had like integral tutorials. We're not on integration yet, obviously, so I guess this is practice. Also, I need an excuse to procrastinate on my work, so here I am. Uh, One of the integrals, or two of the integrals that came up were the Fresnel integrals, and you can't use elementary techniques to solve these. So I'll show my approach that I thought about it, and I'll go through it step by step if you're interested. Again, these are called the Fresnel integrals, and when we're faced with a challenge in math, we either start with an easier, like less complicated version of the problem, or we make it harder. So, of course, it's going to be this one, so bear with me. We're going to take a leap, and then it'll get easier as we go along. I'm going to start with the first one, which was sine of x squared dx, and I'll use r for the real numbers instead of plus or minus infinity because it's just easier to write. One of my favorite integration techniques is to incorporate complex numbers, especially if the integrals come in sine and cosine pairs, because the Euler's equation, it nicely relates sine and cosine with imaginary numbers. So if I call this w, notice that the imaginary part of iw is just going to be w. And what's nice about like stepping up a dimension is that we can sort of mathematically abuse this with like e to the iw plus like b a real number. That this is still w. So like for all a and b in R, the imaginary part of a plus bi is still b. So if you notice here, what I'm going to do is actually this a will become the other Fresnel integral. So I'll just use the cosine, and then I'll tack on an I to the sine. And this x squared over here is going to be a pretty big hint that we're going to be dealing with some form of Gaussian integral, which is like a good target because that has a closed formula anyway. And using these facts, you might be able to sense the next step that I'm going to take here. So let's consider the integral. I guess it's more appropriate to use the infinities because we're dealing with complex numbers now. And we're going to sort of combine both of the Fresnel integrals because we want to make use of that Gaussian integral later on. So if you notice, the real part of this is going to be the cosine version, and the imaginary part is going to be the sine version. So let's recall Euler's formula, where e to the I theta equals cosine theta plus I sine theta. And if x squared is our target theta, then e to the ix squared equals cosine of x squared plus I sine of x squared. Now, this is very close to the Gaussian integral. Recall the Gaussian integral was like e to the negative x squared dx. This is sort of like the negative version. So what we can actually do here is have e to the I negative x squared. So what does that happen here? Well, cosine of negative x squared plus I sine of negative x squared. We just negate the inputs. So why are we going through all this trouble to make it look more complicated than it has to be? Well, the left side is, if we were to integrate it from the infinities, right, this is the complex Gaussian integral, which is really easy to solve. We already have formulas for that. Here I just pulled out the negative there. And then the right-hand side is in a form very close to the integrand of our Fresnel integrals. So actually I'll go up. I'll call this Fs for Fresnel sine, and then I'll call this one Fc for Fresnel cosine. So as you can see, these are very close to those integrals. So let's integrate both sides. And here, remember our negative angle laws. Cosine of negative x equals just cosine of x. So cosine of x squared dx. Here, this is actually just Fc. And then similarly with sine of negative x, this is just negative sine of x. So I'll pull out the negative here. So minus, and then I have an I. And I kind of skipped the step where I integrated the entire thing. I hope you can see that I just split up these integrals. sine of x squared dx. So this Gaussian integral is actually just Fresnel cosine minus I times fs. So this crazy Gaussian integral the real part of this is going to be fc, and the imaginary part is negative f of s. So to recap, why we actually sort of made this more complicated than it looks like it has to be is because solving for this complex Gaussian integral solves for both of these at the same time, which is really nice. So let's go ahead and do that. Recall our Gaussian integral formula where alpha is our x squared scalar. This is conveniently the square root of pi divided by alpha. And actually, I guess I could go over why this works briefly. If we have our normal Gaussian integral, where 1 is our scalar, then this is root pi. And this is a given. If people want, I guess I could make a video, if I have time, on why this is true. But if we want to introduce our scalar, alpha x squared dx, what I'll do is, let's say alpha equals b squared, so that this equals e to the negative b x squared dx. And a cool trick when you're dealing with scalars of your variable, I'm actually just going to multiply by 1 over b and b in the integral. So, but I'm going to multiply the b to the dx operator differential. So e to the negative bx squared d bx. And what's useful about this is that I'm just treating bx as its own variable now. So this is 1 over b. And we already know this is root pi because of this. And if b is the square root of alpha, we have square root of pi over alpha. So that's how we have that. And in this case, our alpha was equal to I, right? And this will be pi over I square root. I'm going to multiply by the conjugate so I don't have to deal with I on the bottom. So negative I, the top is just going to be negative I pi, and then the bottom, this is negative I squared, which is just 1. So nice, we just have the square root of negative I times pi, which looks bad, but we'll simplify it. And this is important, we're remembering this is the complex Gaussian integral that's actually equal to this, not our Fresnel integrals yet. So this is negative I pi square root. And I'm going to split this up into square root of pi times the square root of negative I. And then in terms of finding out what this actually is, I'll recall that negative I equals e to the negative I pi halves, right? So we have our complex plane. Negative I lands here, and this angle is negative pi divided by 2. So then this becomes the square root of pi times e to the negative I pi halves to the 1/2, because I'm taking the square root. And then bringing this into the e power, e to the negative I pi divided by 4. And then this is equal to the square root of pi times, and let's see, this is this part of the circle, so the square root of 2 over 2 minus I times the square root of 2 over 2. Multiplying this out, we get the square root of 2 pi divided by 2 minus I square root of the same thing, so 2 pi over 2. This is square root of pi over 2 minus I, for the equals, pi over 2. And recalling our fact earlier that we found out, the Fresnel cosine is the real part of what we found, and then the Fresnel sine is the negative imaginary part of the complex Gaussian integral, which is what we have here. We see that fc equals the square root of pi over 2, and then fs equals the negative imaginary. So the same thing. And that should be our answer, which is really cool that they're the same thing. And it was weird that we brought in complex numbers. And just for answer verification, Wolfram Alpha says we're correct, so we're correct.